Hello, hello, hello. Hello guys, welcome to today's session on Yebo Tutor, our live online tutorials. My name is James, and as usual, I'll be taking you through some few physics concepts. And for today, we have simply outlined for you to motion under gravity, that is projectile motion. I'm sure you commonly know that one as projectile motion. So in today's session, we're gonna look at projectiles, which is when an object is thrown vertically upwards, and would also look at horizontal projectiles and projectiles that are launched at an angle to the horizontal. So in all those cases, it's motion in 2 dimensions because in this case, we have the motion undergoing x and y displacement at the same time. So unfortunately today my network is not as good as I would have loved it to be. So if you would be experiencing some buffering, please just bear with us. Just bear with us but I'm sure you'll be able to get through the message in terms of what we are communicating with regards to the sections that we'll cover today. Okay, so what we see here already is a question on the screen. So this one is simply a recap of what we did in the previous session. So we'll start with those 2 questions, then we'll go on to today's business. So I'll just start from there and look into that. Then as usual, we'll see a few examples that relate to projectiles and what motion under gravity simply means in the form of simulations. So that's what we are going to do. So our first question, which is showing here, simply says, an object of mass m moves down an incline at a constant velocity as shown in the diagram below. So there are some important keywords to take note of there. Constant velocity. There's a lot of information in that statement or in that part of the statement on its own. I would have put it also in bold, just like m is in bold, the mass of the block. But constant velocity tells us a lot about the motion of that object of mass m. So the picture given there, okay, let me use blue. Okay, so here we are. We have the incline, and the angle to the horizontal is theta. The object is a block, is m, such that mg is the weight. We have the component that is responsible for the action of gravity down the incline, and we have the component perpendicular to the surface, which is the component of gravity perpendicular into the surface, right? Perpendicular into the surface, making that angle. And so if this is mg, this angle here, since this is 90, we therefore know that this is 90 minus theta. So the angle there is 90 minus theta. Then if the angle between the surface and the component perpendicular to it is 90, it simply makes this angle also theta, because this will be 90 minus theta plus theta, making that angle again 90 degrees. So this one is theta, making this component, you remember we said the angle, the component that subtends an angle with the vector is a cos theta component. So this makes it mg cos theta. That's how we get to that. And perpendicular to the mg cos theta component is mg sine theta. The other component, perpendicular. Okay. So we have the reaction. If we can finish on the so when we look at the force diagram, we don't consider the components. Usually it will be just the forces acting there, and in most cases, don't know what subscript you want to use there. I would like to use FR, that's friction, and we have the component normal to the surface, which is what we call the normal force. So the normal force would usually be acting from the surface and is equal but opposite to the force perpendicular into the surface. So it acting to this component which is perpendicular to the surface. So that's how the normal force is given in this kind of diagram. Okay, now the question is such that which one of the following expressions represents the magnitude of frictional force acting on the object? Okay, so already I've given you a picture. The magnitude of the normal force will be equal to mg cos theta to the cos theta component. The magnitude of the frictional force, if this system is in equilibrium, be it static or dynamic, the magnitude of this frictional force will be equal to the component down the plane, mg sine theta. And we have mg sine theta as b. Mg sine theta is b in this case. So the answer to this question number 1.1 will be b, mg sine theta. That's how we get to that. So you don't need to do all the working. I was just trying to explain to you how this comes about, but I'm sure you can follow, and that's the reason, or that's how we get to the final solution, to know that the component is mg sine theta. It's very important to understand where these things come from, what it is that we are referring to as the expression relating to the magnitude of the frictional force. So we're told that this is constant velocity. Constant velocity, we say it is an important term which tells us there is equilibrium in this case. So if it is with constant velocity, then the system is in equilibrium, kinetic equilibrium, right? Such that mg sine theta and the frictional force are equal but opposite. The net force is 0. So if they are equal and opposite, their magnitudes will therefore equate. Okay, so we're done with that part. We will proceed to the next part, which is 1.2, which says a car of mass. Let me just scroll on that question. Okay, there we are. A car of mass m is traveling at a constant velocity and has a momentum p. The driver notices an object ahead of him and applies the brakes so that the momentum of the car changes to half p. So this is half the momentum. Which one of the diagrams below correctly shows the relationship between pi, the initial momentum, pf, the final momentum, and delta p, the change in momentum? So remember, for 1.2, we have pf minus pi equals to the change in momentum. All right? Or in other words, the initial momentum plus the change in momentum, apply a change in momentum, will give us the final momentum. So we have a momentum initially, then we apply a change, we get a final momentum. So this question, final momentum minus initial momentum, is equal to the change in the momentum. Now, we're told that the change is such that the final momentum is half of the initial momentum, right? The initial momentum is simply p, and the change in momentum is therefore what we want to find. And this is a simple expression or a simple description which just tells you that the change in momentum is negative half p. Because if you have initial momentum and your final is half p, then you are removing half p. So change in momentum, sorry, I'm using m there, delta p, the symbol is p, right? Change in momentum. Okay, yes, let's use consistently p, because m is for mass. So delta mv, if you want to use the proper symbol there. So delta p is equal to half momentum minus the initial momentum, which is negative half p. So this is the change. And when we present this vectorially, we have the initial momentum, which is that, plus the change in momentum. So this is pi, initial momentum, plus the change in momentum, which is equal to minus half pi minus half. So that will be minus half p. Okay, so pi is equal to p, right? Then minus half p, and what remains is equal to just 1/2 p. Final momentum pf equals to half p. So we want a diagram that has this. Remember, the length of the arrow gives us the magnitude of the vector. The direction of the arrow gives us the direction of the vector. So the change in momentum, delta p, is equal to minus half p there, should be in the opposite direction, and the final momentum should be in the same direction as the initial, but only less by half. So this is what we want for p, half p, the final, and the change in the momentum. Now, the most appropriate one in terms of our solutions there is, I think you can pick that, you can identify that also. We have B. B is the best choice for part 1.2. So B is the best choice there. B is our best shot. Okay, so enough of these questions. So we've looked at a number of questions on friction, on change in momentum. As we proceed in our next sessions and the coming sessions, we'll look at a number of questions also from past exam papers, so that we have a variety of questions that ask for different concepts or on the same concept but asked differently. So we'll be looking into most of the questions still on these topics, because I mean we haven't exhausted much in terms of what we've covered. And as much as you guys might want to cover other stuff, you are free to join our WhatsApp group. You can send, if you don't know the link to our WhatsApp group, you can just type the message on the comment section on this channel. We'll be able to help you accordingly. But in that WhatsApp group, you will be able to ask questions or even suggest the sections or topics or content that you'd like us to cover with you. So this is how the system works. So the other thing, we have our Zoom. If you would scan, if you can scan the QR code that that is showing above, right? That QR code, if you scan it, it will lead you to our Zoom meeting. So the Zoom meeting is up and running. You are free to join us if you want to say anything or to give us your contribution, or be it ask a question or just give a comment. You are welcome. You can call in, your friends can even hear your voice on the channel. So that will rather be cool. Yeah, that will be cool. Rather, I think you would actually like to hear yourself speaking out on the channel. So you're welcome, guys. You're welcome to converse with us. We want you to be able to chat with us and interact, because interaction is very important. If we interact, there is a lot of things that you learn in the process. There is a lot of things that you learn by so doing. Okay. So let's look at the next question. Okay, so that's our Zoom platform. Yeah, for those that want to join us, I will see you from that platform. You can even use that same platform. You can use that same platform to chat with us, and we'll be able to read your comments on the same Zoom platform. So this is how the platform works. Feel free, guys, feel free to get in touch with us in any way that is convenient to you. Okay, so our next question, a hot air balloon, that's question number 1.3. A hot air balloon is moving upwards at a constant velocity v. A stone is dropped from the hot air balloon. Okay, so we are talking of gravity here. Okay, so that will be my version of a hot air balloon. And usually the people in there. Okay. Then we're told that one of these guys drops a stone. So the hot air balloon is moving upward at a velocity v, constant velocity in this case, and the stone is dropped. So this guy is holding a stone there at that time, and they decide to drop it. Dropping it, it means just leaving it. It's not throwing, it's dropping. So the stone is dropped from the hot air balloon. And what is the velocity of the stone at the instant it is? At this instant, t equals to 0, the stone is dropped. So what do you think, guys? How do we conclude on the initial velocity of the stone when it is dropped from the balloon? So ideally, how will the stone move? Because the balloon is moving with that velocity, the people in that balloon have the same velocity. The stone also initially has that same velocity v. So the motion of the stone is definitely gonna be something like that. So it will start with an initial velocity. It will start with an initial upward velocity. Will also be dropped, yes, but its initial velocity is v, because when it is dropped, it is still moving at the velocity of the hot air balloon. So its initial velocity is v upwards. So the writing is on the wall. Our answer is C. So it cannot be 0. The hot air balloon is not 0. If the hot air balloon was stationary, then the stone will start at 0 and simply drop downward directly at 0 meters per second. Starting at 0 meters per second. But now the hot air balloon is moving constantly at a velocity v upwards, so the stone will also start with a velocity v upwards, right? So you should be careful. You should be careful in picturing or like such situations, such scenarios. You should actually get a clear picture of what is really happening, what is each that I'm supposed to identify from the description that has been given. Okay, so part 1.4 continues to say an object is thrown vertically upwards from point R. So we've got an object thrown vertically upwards. The diagram is there from point R and passes point Q, then reaches a maximum height at point P. So you can see R is at the outright bottom, then it passes through Q at some height upwards and reaches its maximum height at point P. Let's talk about this setup. We said this is motion under gravity or projectile motion. So this object thrown vertically upwards is in projectile motion, but this is just a vertical projectile. So it doesn't describe this path which I've included here, where it makes a parabolic path and then continues downwards. So in this case, in any case, when we are dealing with such motion, we know that the acceleration is due to gravity, g, excuse me, and you have to be very careful in terms of the directions. So you have to assign, it's up to you to assign either at some point you want the upward direction to be positive, in which case the downward direction becomes negative. So that is usually the convention that is used, upward positive, downward negative, but you're allowed, if you want to use downward negative in any instance, you just need to be consistent. Consistency is the key. So in any case, acceleration due to gravity does not change in terms of its magnitude and direction. So if you are going up and upward is positive, it means your acceleration will be minus 9.8 meters per second squared. All right. And if you are going downward and your downward is negative, then you'll use the value of acceleration as 9.8 meters per second squared. Now, if you do the opposite and you use upward as negative, then this one, if upward is negative, it means downward is positive. So the value of g becomes positive. And if your downward is positive, it means, okay, let me rephrase that. If you choose to be negative, upward to be negative, it means the value of g is 9.8 to be positive. If your downward is positive, yeah, something is not tallying there, something is not tallying. So we said if upward is positive, our g is minus 9.8, which is okay. If upward is negative, let me write it, listen to myself saying this. So if upward is negative, then g is equal to 9.8 because it's downward, so it's positive meters per second squared, right? Because upward is negative, so g is going in the positive direction. Then if downward is positive, what's happening there? But that's what I was saying anyway, so it seems I was correct. If downward is positive, then, oh yes, if upward is negative, this one is going in the downward direction, which is positive. It maintains its positive sign. So it's opposite to the velocity. If the velocity is going downward, it is positive. G is also positive. Okay. So in this case, the acceleration due to gravity is not changing sign. Right? So it's unlike in this case when the velocity, in this case, when the velocity is positive and upward, then the acceleration is in the direction opposite to the velocity and is downward. So the acceleration due to gravity, we give it a negative. When the velocity is downward, okay, then the acceleration due to gravity is downward and is still negative. This is where the error was. So it maintains sign. So which means whichever direction you choose, your acceleration due to gravity also assumes a direction depending on, if positive is upward, then acceleration, due to gravity is downward, so it's always negative value. If your downward is positive, then your acceleration due to gravity will also always be positive. Okay, so we've concluded on that. So don't forget, this is very important in terms of direction, because we are dealing with vectors. Velocity is a vector. Direction is very important in fully defining that vector quantity. So it's not only magnitude we're worried about, but also the direction, be it upward or downward, positive or negative. Okay? Now, for the question given, this is an object thrown vertically upwards from R, then going through Q and reaches its maximum at P. Which one of the following is correct as the object moves from point R to point Q, not from point R to point Q, not Q to R, not R to P, not P to Q, or whatever you may think. The question wants R to Q. First part of the choices. It reads, the total mechanical energy has increased. So what is total mechanical energy? The total mechanical energy is the sum of potential and kinetic energy. Does it increase, or the potential changes to kinetic in going down, and kinetic changes to potential in going up? So at the end, in a closed system, the total mechanical energy of the system is conserved, is constant, should be the same. So it can't increase if we don't have any external source of energy, right? So A is out. B, the total kinetic energy at point P is 0. Where is point P? At the top. Oh, that's very true. Very, very true. But what's wrong with that? The question says, which one is correct as the object moves from R to Q? It has not reached P. So don't be distracted. Take note, don't be distracted. C says the decrease in kinetic energy is equal to the increase in potential energy. From R to P, we are increasing potential energy. Yes, that's true. So the higher you go, the higher your potential energy. I'm sure you remember that potential energy is mgh, the height, right? Or the displacement from the ground. So the potential energy does increase at the expense of the kinetic energy for an object thrown vertically upwards. If it is thrown vertically upwards, it means it starts or it launches off with an initial velocity, meaning its kinetic energy is maximum. Then that velocity decreases, its kinetic energy is decreasing, while potential energy is increasing, right? So the decrease in kinetic energy is equal to the increase in potential energy. That is likely true. Then D says, so if we ignore friction, like the last statement in the description tells us, ignore the effects of friction. So C should be completely true, because there is nowhere else where we would lose the kinetic energy too. D says the average work done on the object is equal to 0. Okay, that's not true. Your work is being done, the energy of this system, right? The average work done on the object is equal to 0. So there should be work done in decreasing the kinetic energy of the object, yes. So otherwise, if there was no work done there, then that object should continue going up. So there's work done in decreasing the kinetic energy of the object. That decrease in kinetic energy is equal to the work done. Okay, so our answer is C, our answer for this part of. Okay, let's move on. Maybe let's look at, I don't know if we can look at 1.6 also, but anyway, part 1.5. 1.5. The net work done by a constant force F that acts on an object to increase its velocity. So you see, there's a force in this part of the question, which is increasing the velocity of an object. So if we're decreasing also the velocity of the object from a high value to a lower value, we have to do work also. So it can be friction doing that. In the previous question, that was gravity doing that, you see. So now there is the network done in increasing the velocity of an object, meaning this work done, the magnitude of the work done is equal to half m v squared minus v final minus half m v initial squared, where v initial is 0, v final is just v from 0 to v. So this work done W described there is just half mv squared, because this is 0. Okay. So if that is the network done, the network on the object. Okay. Something is happening there. Something is happening with my screen. I'm gonna refresh this. Okay, there we are. We should be good. Okay, just bear with me a little. Let me just check my connections. Let me just check something with regards to my connections. I'll be back shortly. I'll be back in a moment.